Okay. Hi, welcome everyone to a new Origin seminar today. Today we have a talk by Jake Clark, who did his PhD at the University of Southern Queensland in Australia, and has since then moved on to a Fulbright scholar in Texas. He's going to talk today about planetary systems. And I would like to remind everybody to keep off their camera, just to make sure that everybody can view the talk without any lag. If you have any questions during the talk, please put them in the chat. Then one of the organizers will ask the question, and then the larger questions we can keep to the end of the talk. So thank you, and Jake, the floor is yours.
Brilliant. Thank you so much, Sebastian. Well, g'day everyone. My name is Jake Clark. I am, well, I was going to say a PhD candidate, but I just submitted my PhD, is going through the examination process right now. I think I submitted about 4 weeks ago. So I don't think I can call myself that. But what I am at the moment, I got awarded a Fulbright to come over here to the US, and I'm currently based at the Southwest Research Institute under the guidance of Dr. Natalie Hinkle, and doing some amazing work in the interdisciplinary circle of planetary astrophysics. And so firstly, before I get started, I'd like to acknowledge the first scientists and astronomers on the lands of which I'm meeting upon today here in San Antonio. That is the Tonkawa and the Tapalam Coantecan Nation, and I'd like to pay respect to their elders, both past, present, and emerging. And I'd also like to thank the organizers, particularly Serena, for organizing this session. Thank you so much. So as I just mentioned, I am an interdisciplinary scientist, I guess like most of you all here. And I try to look at the broad picture of exoplanetary systems, the stars that host these planets, and also by using large stellar surveys and large galactic archaeology surveys to then go through and utilize the information that they have to better understand those stellar systems, and then therefore work out and better determine the planets that these stars likely or do actually host. And so before I started my PhD research, I really got involved with following up exoplanets and confirming exoplanets with the radial velocity method. So we can see here a star and planet orbiting around a central point, and we can see that starlight shifting as that star is wobbling around that central point. And it really got me thinking about how important stellar properties are to better understand the planet. I mean, we can see through the equations that to determine the mass of this planet, we have to better understand the mass of the star, right? And similarly, now we have TESS, which launched almost 4 years ago. I can't believe it's been 4 years since that telescope has launched. But TESS is now observing the entire night sky and is observing transits. And again, transits, we are observing the relative flux decrease from the star as the planet passes across the face of the star, as we're seeing right here. And so that relative dip is dependent upon the size of that star as well. And so again, to better understand that system, you need to better characterize the stars. And so that got me thinking about at the start of my PhD in 2017 is thinking about, okay, well, if we're collecting all of this data about all these planetary systems, then we should better understand the stars that are going to potentially host these planets. And so, as I mentioned, we're observing these transit depths, we're observing these radial velocities, and with our models, we can then determine the potential size and mass of these planets. But then actually to do that, we need the stellar information such as the mass and radius of the star. And if you want to work out the habitable zone of a planet as well, you need to determine the luminosity of the star. And to do that, you need to also determine the distance and how far away that star is. And also, if you want to determine the mass and radius of these stars, you also need to work out the surface gravity and the effective temperature to use isochrone models to then develop to then obtain the mass and radius relationships. And not to mention stellar abundances, which I'll talk about a little bit later on, are hugely important now into better characterizing the potential geological and chemical compositions of the planets that these stars host. And so combining all of these observables together, we can then determine the mass and radius of a planet, which we can then work out the density, and then through chemical abundances, we can potentially determine the composition, and through the period of the planet, we can then work out the habitable zone and if this planet is indeed potentially habitable or not. And so it got me thinking about, therefore, how we can construct large stellar surveys to then better characterize stars that are going to be observed by TESS. And we can see the power of homogeneous surveys with the likes of the California Kepler survey, which was able to derive the radius gap that we all know and love now. And we can see on, this is the radius gap here, we see a low of planets around 1.8 Earth radii. And then over here, we can see that Lauren Weiss was a lead author on this paper to show that multi-planet and single planet systems come from the same stellar populations, which is really intriguing. And then I came across some work done by Apogee. So Apogee is a galactic archaeology survey, and they were able to look at the Kepler objects of interest. And then with this homogeneous survey, they were able to, because if you have a homogeneous survey, you have all your systematics are all internal, and you're not trying to, what I'm trying to do right now, go to surveys from all over the place, and you want to try and make them internally consistent, and it's challenging. But if it all comes from the same survey, all of that is done for you. And so we can see here that planets with planets less than 8.3 days tend to be smaller, whereas planets that have an orbital period greater of 8.3 days tend to be a little bit larger. And that's what they were able to determine out of the Apogee data. And what has recently came out is that an increase in stellar abundances is an increase of the probability that you're going to be likely to host super Earths or mini Neptune planets. And I can see Kevin Hardegree-Ullman on the chat as well. And so he's also done some amazing work with the K2 sample as well. And so what I wanted to do then as a part of my PhD is utilize this amazing, incredible information that is right at our fingertips. We don't have to, with the likes of the California Kepler survey, they have to go out and obtain the spectra. And if you have these huge surveys such as Apogee or as GALAH, as I'm about to talk about in a second, you don't have to think about grabbing observing time or have to think about writing proposals because the data is all there. So I managed to start to become a partner of the GALAH team, which I'm still a member of now. And what's amazing is that the GALAH team have been able to obtain the spectra of, as we can see in this plot here, of over 800,000, 700,000 stars across the southern sky. And some of these stars, I'll show you in a second where these stars are located in on a map, but we can see here that there's a few projects that have overlapped with the K2 and with the TESS sectors. And so you'd be a little bit silly to not then be able to utilize this information for exoplanetary science. And so the amazing work that's done with the GALAH survey, we can see here on the left-hand side, this is what came out of the third data release. There's been 3 data releases so far of GALAH, and we just dropped that only last year. And we can see that just with the chemical abundances and working out the galactic dynamics, we're able to find out the mean eccentricity and be able to determine that alpha-rich stars tend to have a lot larger eccentricity around the galactic center than They are then stars with solar-like compositions, and we can also do chemical tagging. And so chemical tagging just means that we are able to understand clusters of stars and be able to link stars to different clusters just by their chemical abundances. And so galactic archaeology surveys are basically trying to better understand the formation and evolution of our own Milky Way. And so this plot here shows the 4 largest galactic archaeology surveys to date. We have LAMOST, we have RAVE, Apogee, and GALAH. And you can see the huge overlap, not only internally within these surveys, but also just the all-sky coverage that these surveys have. And we can see with this particular plot, we can see the TESS sectors, and this was, sorry, I made this about 6 months ago, so it's a little bit outdated now. But we can see that the TESS sectors and where TESS has been observing is in these orange squares here. And each of these purple dots here are actually observations from GALAH. And so there's a huge overlap here of the stars that are being observed by TESS. And what's amazing is that you have this sort of region here called the TESS continuous viewing zone. And so these stars have been almost continuously observed as TESS observes one hemisphere. And so the most planets that you're able to find in these surveys are going to be in this continuous viewing zone, because these stars are continuously being observed by TESS, and therefore you're likely to pick up more exoplanetary signals. And what's amazing now is that TESS is has now started to observe the ecliptic plane, and we can see here the K2 fields that were observed by the Hermes instrument, which is the same instrument that GALAH uses for the collecting spectroscopic collecting spectra from the stars that it observes. So it was sort of a no-brainer then for me to then start asking some questions about what I wanted to do for my PhD, and by utilizing the information that we already have available. And so what I wanted to really find out is that what can we learn about current exoplanetary systems orbiting GALAH stars? So stars that are already known to host planets, what can we actually learn by using these large stellar surveys? And then can we actually forward predict the types of planets that these stars are likely to host? And so those are sort of the 2 big questions that I was trying to answer throughout my PhD. And so I got onto the TESS import catalog. And so every huge survey has an import catalog, which will create a catalog of stellar parameters for the stars that this survey is going to observe. And so here, this is from the candidate target list. So this is a subset of high priority targets that were set out by the TESS mission team that they were then going to go off and observe. And what I noticed is that this is from the TESS import catalog version 7. I cross-matched that with GALAH's second data release, and I noticed that there were some stars that were misclassified. And what I mean by that is on the left plot here, we can see that this is the surface gravity taken from the spectra from GALAH, and this is the surface gravity calculated from the TESS import catalog here. And there was a huge discrepancy of surface gravities around here, which if you put through an isochrone model and translate that into a radius, you'd have a lot of stars here that could have been misclassified, that were misclassified giants. And if you look at the transit photometry model and do the calculations, a star that is out here and you find a planet that's the same size as Earth is going to be 3 times as large if you're going to use this catalog as opposed to this catalog. And so there's this huge discrepancy. So if you want to better characterize the planets, having accurate representations of what the star actually is extremely important. So what I wanted to do is then I wanted to create a catalog that would be useful for the exoplanetary community of not only physical parameters that we can use to calculate the mass and radius of these planets, but then also to calculate the chemical abundances of these stars as well. Because what I was noticing, and I'll go through in a second, is the importance of stellar abundances to determining the compositions of potential rocky worlds. And so what it is I collected the data from GALAH, and that was the surface temperature, surface gravity, the iron abundance, and the alpha abundance. And the alpha abundance is extremely important to accurately model stars on through isochronic models. And then I also used Gaia parallax and magnitudes, along with magnitudes from 2 mass values, and I inputted that into an isochrone models known as isochrones. And those magnitude bands were essential to model the star's spectral energy distribution, which is important to then model the star's radius, along with the mass and luminosity, age, and Hubble zones that would come out of this analysis. And not only that, but I also grabbed the GALAH's chemical abundances, and I also calculated the abundance ratios, which are important for these geological models. And so this is known as the GALAH TESS catalog. And so I have 47,000 stars within that catalog. And if you go onto the Data Central website, datacentral.org.au, you can download the catalog there. And I'll have this PDF available for everyone. And there's all clickable links here. So you can see down the bottom there, that'll take you straight to the catalog there. So as I mentioned before, determining and making sure the star's characteristics are accurate is really important to then making sure that making sure that the planet's mass and radius is also accurate. So what I wanted to find out first is that if you had a 1 Earth mass and 1 Earth radii planet, an Earth-like planet, with the stellar parameters derived by GALAH, how different would this planet be if you were to change it to different stellar parameters? And so for this example, I just changed it from the GALAH stellar parameters to the stellar parameters from the TIC, just to see what difference would it make. Just thinking that would probably make a difference within error bars, but it turns out it made quite a large difference. And so we can see here that there's quite a large spread, not only in mass, but also in radius. And an average error bar in planetary radii is about 10%. So for some of these stars out here, for some of these misclassified stars here, and therefore they're misclassified planets, this Earth-like planet wouldn't be Earth-like at all. We would have this huge volatile layer and probably would be coreless and would be nothing like we would think an Earth-like planet would actually be. And so I think it's important for the community to therefore, there's no real right answer as to what stellar parameters we use, but I think there needs to be some sort of consistency. If we are going to say, hey, look, we've found this planet that we think might be Earth-like, then it's important to determine, okay, well, through other parameters, is it truly that size and mass, or is it just the way that those stellar parameters have actually been derived? And what's really cool now is that the NASA Exoplanet Archive, which I use on a daily basis to obtain stellar and planetary parameters from, you have not only one option for your planetary parameters, but you have multiple options here. And so we can see here for the planet HD 97658b, oh my goodness, that's a mouthful. We can see here that we have multiple different planet and mass radius values, and we can see here that there's multiple transit depth values here. And again, so you have to ask yourself the question, well, what parameters should I actually use here? And I think that's a discussion for another day. But what I wanted to do with the newly derived GALAH data release 3 is that with new stellar parameters from the latest release of GALAH, and with the NASA Exoplanet Archive now releasing multiple multiple values of transit depth and semi-major amplitude is that can we actually bring all this information together through a weighted mean approach to actually better characterize these planets? And so a paper that I just published last month has shown that, for example, with Queensland 7b, I was able to utilize multiple values of the transit depth and multiple values of the semi-major amplitude of the radial velocity to then bring down Queensland 7b's mass and radius. Its radius is now down to about 3% and its mass is down to about 9%. And so we can really hone in and characterize this world better than we ever have before. And what's really interesting is that now sort of leading towards this radius being in the middle of the radius gap as well. And the composition of Queensland 7b might entail a volatile layer now, considering its radius is now a lot larger than we would consider just a rocky ball to be, which is really, really interesting. So that's what I was able to do with the latest GALAH data, along with better revising the parameters of well over 200 other planets. And what's really great with this extra information that we have is that the GALAH data release is able to obtain the stellar rotation, or the V sin I, of all the stars that's able to collect. And so I was able to cross-match that with the NASA Exoplanet Archive and known TESS objects of interest and K2 objects of interest. And what I wanted to do is I wanted to calculate, one, what's the stellar rotational value, because what happens is that if you want to follow up stars and confirm their masses, you need to have a nice stable star. You need to have a star that's slowly rotating, because if a star is a fast rotator, it blurs out the precise lines that you're going to use for determining the radial velocity measurements. And so in order to just get a few observations of that star to then calculate and confirm the planet, you need tens or hundreds, or in some cases, maybe thousands of radial velocity measurements to then actually obtain the mass of the stars. And sorry, the mass of the planets, I should say. And so these are the orange, sorry, the purple dots here are planets that have confirmed masses, and all the orange dots here are planets that have no confirmed mass measurements. And I use the Chen-Kipping mass relationship to try and determine what their potential mass would be, and therefore what their potential radial velocity sampling amplitude would therefore be. And so this is showing, particularly in this region here, that most of these planets would actually be really difficult to follow up with radial velocity measurements, and that this is another great tool for follow-up teams, especially with the TESS mission, to then utilize these stellar catalogs to go, okay, well, this star's V sin I is 10 or maybe 20 kilometers a second. This planet's semi amplitude is probably about 2 meters a second. So we're actually not going to waste our time with this particular planet. We're actually going to go off and try and find a planet that we can actually go and detect the mass of. So just shows another great way of being able to utilize these surveys. However, it can be done. And so a paper that I've just submitted is the confirmation of a planet TOI 778, and its host star has a rotation velocity of almost 30 kilometers a second. However, this planet is about two times the mass of Jupiter. So it is a very large, hefty planet, but it can be done, and you can find massive planets around rapidly rotating stars. And we're actually also able to determine the Roster-McLaughlin effect and able to determine the spin orbit alignment of that system as well, which was really, really neat. And so now I'm going to move on to, I've shown you the benefits of being able to determine the physical parameters of planets through the physical parameters of the stars. However, now I'm going to show you what is really, really awesome, and being able to utilize the chemical information of the stars to then determine the stellar populations and determine, okay, is this planet around a star that's within the thin disk or thick disk, or as I've been mentioning, can we use those stellar abundances to determine the composition of these worlds? And so we know that the galactic plane consists of two disks, the thin disk and the thick disk. But more and more information is suggesting that there aren't really two distinct disks, and that there's actually a gradient from the thin to the thick disk there. And so what I wanted to do is I wanted to determine, okay, how many of my planets are orbiting around thick disk stars, and how many of them are orbiting around thin disk stars? Because what I wanted to really find out is there a population difference between the planets that we find around thick disk hosts compared to thin disk hosts? And so you can do that by using chemical abundances, and you can use, say, you can see here that I was able to use the iron abundance and the magnesium abundance and the alpha abundance as well, along with the kinematics and dynamics of the stellar systems. And so this is the radial velocity of the star, and this is the perpendicular and azimuthal velocities of these stars. And so we would consider a star to have a thick disk-like kinematics if it's beyond this teal line here, and this here is the dynamics of the stars as well. And stars that sort of fit within this top corner here are stars that you would think would be considered thick disk host. However, here the ones that are highlighted or with a black accent around it, those are planets that, stars that I thought were thick disks chemically, using this cutoff line here, which is from Michael Hayden 2016. And you can see that some stars would have thin disk kinematics but have thick disk chemical abundances. And so it's actually really difficult to then just use one without the other to then try and determine if stars are actually associated with the thin disk or the thick disk. And so I used a conservative method to actually use both, and only found a handful of hosts that were a part of the thick disk. So unfortunately, with only 5 planets, there's not a lot of demographics that you can actually do with that. So stay tuned for more information of being able to collect more information from other surveys to then better find thick disk hosts. And also we tell ourselves that stars and planets are formed out of the same disk of gas and dust. And so the refractory elements of the stellar photosphere of the host star is somewhat similar to the planets, the refractory elemental abundances of those planets that are hosts. And so what we can do is that we know that for a planet like our own, the mantle is comprised of solid silicate minerals, and we know that to first degree order that the core is made out of liquid iron. And so if we can determine the mass and radius of a planet, we can determine the density. And so we can roughly determine what the potential composition could be. And so here we have the TRAPPIST-1 system. However, what Unterborn and others found in 2018 is that if you combine that with the chemical abundances of the planet hosts, and they were able to find out through the chemical abundances of other M dwarfs to then infer what the chemical abundance of TRAPPIST-1 might be, you can then work out, okay, well, this is what the ice layer might be, or this is what its mantle can be comprised of, and this is what the core size could be. And then you can then go another step forward to then try and work out plate tectonics or other potential habitability indicators that you just don't have if you just have just the mass and radius of a planet. And so what I was able to do with the GALAH catalog is that I was able to determine the stellar abundance ratios of the magnesium to silicon ratio and the carbon to oxygen ratio to first order determine what types of rocky worlds GALAH stars are likely to host. And so this star here represents our system. This is the stellar the solar abundance. And so roughly about half of the planets that we're likely to find around GALAH stars, the rocky planets, I should say, are going to have compositions sort of similar to those found within the solar system. But we can see here about another half are going to be planets that have geological compositions that are unlike anything that we find within our solar system. So one, that is really, really cool. And two, it's just another thing that we need to consider of, okay, we may have just found a planet that's similar in size and mass of our planet, but it might not actually have the geological material needed for a planet like ours to thrive upon. And so it might be a little bit more complex than just simply equating these abundances from their stellar host to their planets. And I'll show you why in a second. And we can see here, this is a ternary diagram, just showing where these stars lie, all 47,000 of them, and sort of give you an indication, sort of Mercury would be sitting down here. So that, again, this sort of shows you that planets like Mercury are sort of atypical, and there must be sort of some secondary process in order for those, for planets like that to occur. If you're just going to use those chemical abundances and equate that to the stellar abundances and use that to equate for the planet. However, recent research, Plotnikov and Valencia have shown that, so this line here shows that if you equate the stellar abundance of the host to the planet, planets should sort of sit along this line here, which most sort of do. However, you have these planets around here, which goes to show that there's not this sort of one-to-one relationship, and that you might need to consider devolatilization, which Wang and et al. Have shown in 2018. We sort of assume that, these refractory elements, the stellar abundance is going to be equal to that of the planetary abundance. But we see here there's about a 10 to 20% difference due to devolatilization. So that's also another thing that we need to consider, is that if you do grab the stellar abundances, being able to devolatize them is probably pretty important. And what's really awesome is that Atabekian et al. 2021 has shown that there might be some sort of gradient, and there's not this sort of one-to-one relationship. So there's more work to be done in this space. And I think also something to consider is what solar normalization are you going to use? I mean, typically we might use LOTAS, or we might use something else. So here I showed sort of 3 different solar normalizations. And so this is for my GALAH test catalog. Just using different solar normalizations actually give you vastly different distributions of what your carbon to oxygen ratio and magnesium to silicon ratio might be. And I'm not saying that one is better than the other here. I mean, that's for someone else with a higher pay grade than me. But what I do want to suggest is that maybe showing different abundances with different solar normalizations might be the trick, or even, just showing what solar normalization you're using within your work can then help us to determine, okay, well, is this a carbon-rich star because it is carbon-rich, or is it just due to the solar normalization that we are utilizing here? However, it just goes to show that trying to use chemical abundances to then infer the properties of the host planets is actually really, really complicated and is still evolving as we're learning more about it. However, we try and do some demographics with what we can. And so a paper that came out a couple of years ago about the conformation of TOI 1444b showed that hot Neptunes tend to favor iron-rich stars. And so what I wanted to do is I wanted to show, okay, well, I have some ultra-hot planets that I showed you with Corat 7b. And I have a couple of ultra-short period hot Neptunes. Is there actually this discrepancy? And actually, is it just iron, or do we actually see that in other elements as well? And so this is where, again, we see these plots. And I should have actually explained this rather than just passing through it last time. But we have 4 different populations of planets in these plots here. We have ultra hot rocky. So ultra hot is just a planet that's orbiting around a star less than 1 day, and a hot planet is just a star that's a planet that's orbiting around a star every 10 days. And so they just plot along here what their stellar iron abundance is compared to their stellar magnesium abundance, and then over here we see the stellar iron abundance and the alpha abundance here with the associated error. So we don't have many. I don't have many ultra hot rocky or ultra hot Neptune planets to confirm either way if that's the case, but we can see here through this plot that they do tend to favor iron-rich stars. But however, there is one particular ultra hot Neptune that unfortunately didn't have an alpha abundance measurement in GALAH, but it did have a magnesium abundance, and it's orbiting a pretty iron poor planet. So it might just be the fact that we might have very few planets here to try and make this distinction. However, what I wanted to do, as I've just mentioned, is that can we look at other chemical abundances and see if there's a discrepancy between these hot rocky worlds and these hot Neptune worlds. So I used a statistical analysis, a KS test, to then try and work out if there's any type of discrepancy between these two populations of hot rocky worlds and hot Neptune worlds. And it turns out that there wasn't. Out of the 28 different stellar abundances that I had within GALAH DR3, only 3 were statistically significant of having 2 different populations. And these are the 3 abundances that came out to have a statistical significance greater than the threshold to show that there might be some difference. And I think the biggest difference here is yttrium, and yttrium is used as a chemical clock. So stars that are higher in yttrium tend to be younger stars, and stars that are older tend to have lower yttrium abundances. And so what we're seeing here is that hot rocky worlds tend to favor younger stars, and hot Neptunes tend to favor older stars. But again, this might actually show that if there's only these 3 abundances that seem significant and all the rest seemed had no statistical difference, maybe hot Neptunes and hot rocky worlds are actually coming from the same populations, and maybe hot rocky worlds are actually just hot rocky worlds are just hot Neptunes that have just had their atmospheres stripped away. So there is some evidence there within the GALAH sample. And what I want to touch on finally is what I'm trying to work on as a part of my Fulbright experience here in San Antonio, working at the Southwest Research Institute. And so my PhD supervisor, Natalie Hinkle, was able to use sort of a classification algorithm, sort of a bit like Netflix. You turn on Netflix and it knows exactly what you want to watch because it's got all your background knowledge of, okay, you love 50s country movies, and then it recommends you a movie based upon what you've watched, and then up comes Big Jake and you're going to go watch that. And so we can utilize a classification algorithm instead of just picking out your favorite movies. Is okay, well, if we know that these types of stars host these types of planets, can we then actually forward predict what types of stars are going to host these planets, and therefore go off on a sort of a fishing expedition to then confirm if that's the case? And so Engel was able to use the Hypatia catalog and utilize different chemical abundances from volatiles, lithophiles, and ceridophiles to then classify what stars are likely to host giant planets. And we can see there was a great list here of predicted giant planet hosts. And what was really awesome is that this is sort of the importance factor of what elements are important for giant planet hosts. And it seemed like it just wasn't iron as what was being told for the last sort of 20 years, but carbon and oxygen also play an important role in the hosts of giant planets. And so what I'm trying to do now is I'm doing that, but with hot Jupiter hosts as well, and looking through the TESS light curve data to then be able to confirm with these higher probable stars if that's indeed the case and they do host hot Jupiter worlds. And so the future is super bright in this sort of niche field that I'm in. And so what else can you do with this? And that picture is gorgeous and sort of makes me miss home of the southern hemisphere and seeing the Magellanic Clouds out and about. But what I'm actually trying to do at the moment is trying to follow up thick disk hosts and trying to find planets within the SMC and LMC with the Galactic Archaeology surveys that we have available. I'm also working on creating a chemokinematic map of planet hosts throughout the galaxy. So utilize all of the surveys that we have to then not only have just a handful of stars that might be associated with a thick disk, but hopefully to have hundreds of hosts to then be able to work out different demographics. And then what I'm working on as a part of my Fulbright with trying to predict hot Jupiter hosts through these classification models. So I'll leave you with my takeaways. Thank you so much for taking the time out of your day to hear me chat, and I'll take any questions that you have. Thank you.
Okay, Jake, thank you for your talk. Are there any questions in the audience? Please raise your hand, or you can also put them in the chat. There's a question by Serena.
Yeah.
Yeah, I'm just wondering about the solar normalization slide that it was. Could you actually explain a little more about how the solar normalization is done?
Yeah, for sure. Just give me 2 seconds to get back to that slide. Sorry. Okay, so if you just have your chemical abundances and you use different solar normalizations, you'll just have a shift in the abundance that you have. But because these abundance ratios, or sometimes they're often referred to as molar ratios, because they're linear, you'll actually get this big shift in, because you're going from log scale to linear scale. So you have these these shifts in your distributions as we see here. And so I can show you. Hang on. I know where the plot is, but I might have to go on the net. But I'll send it through to you. Just a plot that I made in the first paper of the GALAH TESS paper, of how different solar normalizations just sort of shift this distribution. But then if you go through and use this linearization, then these distributions are going to be a little bit different. So hopefully that does answer your question.
Yeah, so I was wondering, if you look at the left and right, the different, of course, abundance ratios. So the left-hand side, if you see that the Anders 89 was different compared to the other two, and then that is not the case for the right-hand side. So I was wondering what's causing that.
Yeah, so it's just simply the way that they've measured those different the different solar abundances. And so here with, say, Asplund and Graves, they have found out that the solar abundance of carbon and oxygen are actually quite similar, or more importantly, the difference between them is quite similar compared to Anders, which is they measured something that was very different between these two. And similarly, we can see that Graves and Anders found a very similar difference between the magnesium abundance and the silicon abundance. However, we can see that this one here has a larger difference in the magnesium to silicon, and therefore those spreads, those distributions are actually a little bit are different.
So I guess that depends on the observation sensitivity.
Yes, yeah. So that just all depends upon how these solar abundances are actually calculated. And I mean, there's a huge amount of work that goes into these to these calculations, and these papers are all like 50, 60 plus pages long. And yeah, so there's a lot of work that gets done. And so, later models inject non-thermal equilibrium equations into the models as well. And I guess it all goes down on what solar model you use and all the rest of it. So it is very, very complicated.
All right, thank you.
Thank you.
And I can see that Caitlin also has a question.
Hi, thank you for a very, very interesting talk. I apologize if you said this and I missed it, but I'm just wondering what you do about understanding the presence or absence of binaries in your sample.
Yeah,
of stars.
That is an excellent question, and something that I sort of brushed over. Actually, no, I didn't even talk about it. So thank you for bringing that up. And so every GALAH data release comes with little bit flag masks about the quality of the spectra. And so the pipeline, therefore, for different reasons, calculates a different bit mask as to whether or not the spectra is good or not. And so spectral binaries are actually found within the process of being able to calculate the stellar parameters. And so there'll actually be a bit mask for binaries. Now, that's not to say that's going to be 100%.
Well, so sorry, let me just clarify. But if you're talking about contamination of the spectra, that would really only be what I would think of as an SB2.
Yes.
Right. But of course, a large fraction of spectroscopic binaries are SB1s, and so unless you have multi-epoch data, you wouldn't see them in that by the characterization of a single epoch, right?
Yeah, that is true. And so there are multiple observations from GALAH. So GALAH sometimes goes back to different observing fields, and then there are multi epochs, which are then taken into consideration and say, okay, well, this looks like a spectroscopic binary. But yeah, that's a great question in terms of SB1s. There isn't a lot that I have done, and I guess that's something I would need to consider. And what would you do in that case? I guess one thing would be that you find this binary and go, all right, okay, then maybe we have to go back and reanalyze this spectra, and therefore determine what the stellar properties are of both of them, and not just the combination.
Well, there's a few things that come to mind. So one of them is that it could certainly change your measurement or your inference on the radius of the planet because based on an eclipse depth. Because you're looking at the light from two stars, not one.
Yes.
So that's one thing that might matter. And then the other thing is that there are correlations between frequency of binaries, the binary occurrence rates and metallicity. And so, and then there's also the fact that binaries typically are less likely to host planets depending on their period. So, when you're comparing a sort of non-planet host sample to a planet host sample, it's important to understand that the sort of typical metallicity properties of those two samples may be a little bit different. But there's just a whole host of ways that might come into play. So something that Maximo is the first author on our papers on this subject. It can really change your inferences about occurrence rates and things like that. And you mentioned at some point maybe doing some cross matching with apogee, right?
Yes.
Yes. So those, there are very good binary catalogs for apogee. So.
Yeah. I might, well, if you could link me to the papers to then, I just miscalled, sorry, I didn't quite get the name of the person who you said.
Yeah, sure. Yeah, I'll send a link.
If you can send me that information, that'd be amazing and make my science even better in the future. Thank you. But in terms of apogee, that's what I'm working on now. And I'll definitely look into those binary catalogs. Thank you. Maximo, thank you.
Okay, so any other question? Sebastian, I think we can probably.
Yeah. So if there are no more questions, then I would like to thank everybody for joining our Origin Seminar today. Next week, we will have our next Origin Seminar, and I hope I will see everybody again next week. Thank you.
Okay, let's. Thank you, Jake.
Thank you so much, everyone.